It's wonderful to have another podcast with real dear friends of mine. And so I'm really happy that Paul Rudd, Jack Lilley, and Caelan were able to join me today and have a long discussion about test blocks, test bars, mechanical properties. What do they mean? Why do we test every heat to make sure it has the mechanical properties required by the specification? What does it mean to make different kinds of test blocks? And so this was really the first of a series, I think, of podcasts we're going to have. The first one, the one we did today, was really concentrated on why is this written into the specification? What does it mean? And how does the mechanical properties, the test bar that we test as a requirement in specifications, how does that relate to the properties we might expect in the casting? What guarantee does a designer have that the properties we get in the test bar actually are the exact properties in the casting itself? So I hope you enjoy our discussion today. And we certainly intend to follow up with at least two more discussions. One is on what does the mechanical test mean, and then how do we understand the manufacture of the test block that we use to evaluate properties. So I hope you enjoy it. Please let us know if you have other questions or you'd like to comment and dig deeper into other subject matters related to this. This is some slides that I put together for test blocks, test bars, and casting. There are some fundamental things that I face almost every time someone talks about test blocks and test bars. And as Paul and I've talked about, this is one of the most common conflict areas for us with customers. And a lot of it has to do with some fundamental misunderstandings. So for those who are watching the podcast, this test block material is actually on the SFSA website under test coupons and casting properties if you go to the free resources. And there's a lot of information there, but there's things that we've done since then that I need to do updating on that. But the first thing I want to do, which I think is really critical, is that we have underappreciated the movement to numerical methods from analytical methods and how that affects the way we do design. And because of that, a lot of the misunderstandings have to do with a failure to really understand those differences. So this is some extractions from the ASTM A148 standard from 1936. And the reason I put it up there is because the reason we do test bars has to do with the inability to do chemical analysis. Ed Kaczmarek, who is about my age, about 65 to 70, actually did wet titrations when he worked for Grady. And a wet titration is the way you used to do chemical analytical things. So you would take a piece of steel, you dissolve it with acid, and then you have a special chemical composition of the liquid in the tube, and you'd measure how much of that liquid it took to change the color of the titration. And when you did that, you could back calculate how much of a particular element was. So you had to do this wet chemistry test on dissolved steel for each element you wanted to analyze. So in 1936, the only two elements that were required to be analyzed were phosphorus and sulfur. That was it. If you specified elements, you could specify those elements if you wanted to, but normally I got to pick them. Just like ASTM 148 today, I got to pick the elements as a manufacturer. But if you specify the elements, then I had to analyze all of those elements. If I had to analyze all those elements in wet chemistry, I wouldn't have a chemistry for your material for 2 weeks. It just wasn't going to happen. It's going to take that long to get in the queue and get analyzed. It just took a long time. And you wanted the steel. So it was really easy for me to get you the steel. And so you can see from this that the tension test was a requirement. So chemistry, all I had to do was phosphorus and sulfur, but tensile tests were required. And that was because the tensile tests were not intended to tell you what the properties of the casting were. They were trying to make sure that the heat of steel I made, the liquid steel I poured into the mold, was capable of meeting the properties of that grade, since I didn't know the full chemistry. That was the purpose of the tensile test. Paul, what do you think of that? I mean, you're old enough. Did you do wet chemistry?
I'm old enough. Yeah, I did some of that. But my understanding, the test bar back then, when you're talking about, the only reason for the test bar was to assure that the chemistry would respond to a heat treatment. That was the only reason that they had these test bars. That was the primary reason.
Yeah, one of the artifacts, and that's what this slide ruler is supposed to show. I actually had to do a seminar for the BAE systems because they're upgrading the M88 tow truck for Abrams tanks. And that's a cast body. And the people who are there today believe that it should have properties everywhere and be completely sound. And yet in the plate sections, the radiographic requirements are level 5, which is the poorest quality that you can specify. And because it's the poorest quality you can specify, it means the designer was required to put something down, but he doesn't care. That's basically what it means. And when I talked to them, they did not realize that when you design these materials, you designed it with a slide ruler. You had a 2D drawing. You didn't have a 3D model. You had to imagine what it looked like in 3D because you only had a 2D drawing. And the designer could not analyze that complex geometry. He couldn't put it in a finite element analysis and find out where the stress concentration was. He had to pretend it was a beam or a plate or a bar because he had to have something that was analytically nice, where he had a formula in his mechanical engineering handbook to calculate what the load was. Not only that, because he wasn't looking at local properties, he had to assume that you had some minimum level of properties everywhere, not because he thought that was true. He knew that wasn't true. He was used to working with materials with knots in them and castings that had porosity in them and inclusions. He was used to that. He knew that wasn't a true statement, but he was just pretending it was a beam or a plate and using his slide rule to calculate whether or not it would meet the requirements. And the numerical methods inherited this assumption of uniform properties. And so most of our customers, our design engineers, believe that materials should have the same properties everywhere, which is clearly just not true. It's so clearly not true. It's not just a casting issue. It's also a forging and a plate issue. So ASTM plate, bar, and sheet specification, the oldest specification that's still active in ASTM. One of those odd things that people don't know is that the ASTM standards are sequentially numbered. So the lower the number, the earlier the standard. And so ASTM A6, A is the steel committee because it was the first committee. 6 mean this is the 6th standard that ASTM ever wrote. So this standard's like 100 years old. And they put in Appendix X2 that says that the tensile test requirements are only intended to characterize the tensile properties of the heat of steel for determination of conformance to the requirement. It's not intended to define the upper or lower limits of test properties at all possible locations. It's well known and documented that the properties will vary within a heat and within an individual piece of steel as a function of chemical composition, processing, test procedure, and other things. This is well-known stuff. And yet many of our design engineers don't know this and don't think it's true. This is also true about specifications. So Vic B. Hall, who used to be at Dominion Castings, was chairman of our specification committee when I started 40 years ago. And he was insistent back in 1983 when we were writing with the Europeans and the rest of the world general technical delivery requirements, ISO 4990, of putting in this statement that the test results from the test blocks for steel castings represent the material from which the castings have been poured. They don't necessarily represent the properties of the casting, which are affected by solidification, rate of cooling and heat treatment, casting thickness, size, and shape. So this is fundamental stuff. And so if you want a test block, if you want to know what the test material is, ASTM A703 says, look, if you get the properties from the test block and you want to know what that means in some heavy section test casting, go buy yourself a Steel Founders Handbook and look at pages 1535 through 1543 and figure it out. So that first document that I showed on test coupons really tries to give this kind of information to people of, if I have the test properties in a 1-inch section, a keel block, what does that mean if I have a 4-inch thick section or a 12-inch thick section? There's only one exception where in ASTM, we require a thicker test block, and that's in ASTM A148, which is still alive. The A36 standard I referenced was 148. This is the same standard. And there they say this was something that Malcolm and I had to do, because in ASTM A148, you order the properties, you allow the producer to determine the composition. So if you're making a thick section casting and you qualify the casting with a keel block, you could use carbon steel to make something that was going to be 8 inches thick, and it wouldn't have the properties in the center, and you might think it should have the properties in the center. So to warn customers and to make the specification more, you're supposed to, if you ordered A148 and you're the customer, you have to identify the ruling section thickness, the thickness. Now, customers often think that I should know the thickness just looking at the casting, but that's silly, because there are parts of the casting he doesn't care about, and there's other parts that are critical. And if he doesn't tell me the thickness, I don't know it. So if he doesn't tell me the thickness, this requirement doesn't apply. If he doesn't tell me T, I can do anything I want. But if he tells me T, then I'm supposed to use supplementary requirement S15 from 781. And S15 limits that to a 15 by 15 by 5-inch test block. So that's the largest test block. That's the only place that thick section test blocks are required, because casting users are supposed to be knowledgeable enough to understand how to translate the properties from the 1-inch bar, knowing the heat treatment, the composition, the hardenability of the alloy, how that affects the properties through the section size. They're supposed to know that. So Paul and Jack, one of my passions is to get us back to the 1930s in terms of the reputation of steel castings, where people recognize that steel castings are the premium product. You can get the most complex, highest performance out of them, but you need to be a really good engineer to do that. You can't just buy it like it's a sack of cement. You've got to really understand how that casting is going to be produced. There's one other slide that I wanted to show, and that is the Sharpie impact. These requirements for ASTM A352 are really clear that the test block properties don't tell you what the toughness of the part is. Okay? No assurance is offered that compliance with the requirements to do the CVN testing will say that the material will resist brittle failure under all possible conditions. It may be that it's supposed to give you some assurance that this is good at low temperatures, but CVN won't give you the information you need. The literature shows that the notch bar impact strength differs widely with many different variables. Consequently, there's discrepancy. So if you take a test bar out of the part, you won't get the same properties. And the committees responsible had the objective of trying to make it mean something, but in ordinary steels, ferritic here is the boiler code terminology. It includes martensitic steels and other steels that are not austenitic. Ferritic steels, it's impractical to remove test bars of over 4 inches and expect them to show results. But I just wanted to share those preliminary remarks to you and allow you to comment on that. But I run into this all the time when there's a dispute between a customer and one of the foundries or a user in the foundry, either because of a failure or because of a concern, and they pull test bars out of the casting and expect them to have the same properties. I normally have to go through this whole litany that the test properties are really to determine the quality of the steel heat, and that the properties will vary in the casting.
I think it's a matter of customer expectations and education, as you point out. Because one of the things in my tenure with Wisconsin Centrifugal is that the engineers and the metallurgists spend a lot of time in the contract review phase understanding what the required test equipment is and what its expectations are. You know, whether we can even use a keel block, because being centrifugal, there's a bunch of products that are qualified with centrifugally cast material, whether it be separately cast or integral. And certainly the customers that are requiring integral material are expecting integral material to have the properties of the castings. So there's different levels of expectations, and maybe because of that process difference, it's a little clearer in that market. But I just wanted to offer that point.
I think that's right. And one of the key things that all the producers, all the makers of steel castings need to know, you really need to read the specifications carefully. Because if the specification says they can pull a test bar anywhere in the casting and you have to meet it, and you agree to that requirement, shame on you. That's your problem. That's not the customer's problem.
Well, in most of those products where they expect that, first articles are required with extensive cut-ups to produce enough data to satisfy that mutual assumption.
Oh, I think that's right. And we,
you know, certainly anything for FAA are full cut-up qualities, firm fixed process, and that's the way they're made. And it's really, you know, we talked a little bit in heat treatment last week about oil quenching, and we have some parts that are oil quenched because that's the spec, and FAA doesn't want to change it. And you know, it's an act of God and 3 Congresses to try to get anything changed. And again, full cut-ups and everything. So it's arduous to change.
One of the ironic things about aerospace, having been on the DoD committee forever, is that at one level, it's really difficult to get qualified. On the other level, it's easier than any other process in any other place, because they qualify each individual part for every aircraft. And so it's not, and so once you have made that first article and it's been approved, you can't change anything about the way you make it, and you can't change anything about it. But you can qualify anything from additive manufacturing to powder metallurgy or anything if you can meet the tech warrant holder and the technical people's judgment that it will be acceptable, and then you make it through the qualification testing during the full engine test, then you're good as gold until you have a failure, of course.
Yeah. Well, thankfully, we've never had a failure.
Yeah.
No. Well, I mean, you say that, yeah, but although I have to confess that every time I hear a news article about an engine failure, I get a little pucker going on until we find out what part it is.
I had the same thing when we had the blowout preventer down in the Gulf, but the big confidence I had was with the API requirements that they were all going to be forging, so I didn't have to worry about a casting being the blowout preventer failure they had.
Well, every 737 has one of our components on it, and we fly them all the time. So, I mean, I have confidence in the product.
Yeah. So, Paul, what kinds of customer interactions have you had where people expected to get properties everywhere and they pull a test bar and it doesn't meet the minimum spec?
Yeah, there's 2 different approaches that I've seen. One of them is what they do is if you have a specification for, say, strength or ductility, Sharpie V-notch, whatever it is, they downgrade by roughly 10%. And I don't know if there's any magic in that number, but if they pull a test bar out of a casting, they expect it to be within 10% of the specification level. So that's one approach I've seen.
Let me ask you a question about that. Does that work for you? Have you had problems with that where I can see if they pull it in the center line or something, you could have a problem, but that doesn't seem completely unreasonable.
I haven't really heard of much of an issue with that, as long as there's agreement about where the test bar is to be taken. That's a critical issue, obviously. So if there's agreement there, I think the 10% is probably reasonable, but I haven't seen an awful lot of data. I just know that I don't see a lot of customer complaints when they take test bars out of castings when they have that restriction.
Do they require you meet the elongation? I remember one big customer that has yellow equipment used to require you met 80% of the yield strength, but they didn't care about elongation because they didn't expect you to meet that requirement. At least that was my understanding.
That's another way of doing it. Yeah. Another thing that I've seen is they basically have two. If they write a specification for a steel casting, they'll have the properties from the test bar for, say, a 1-inch coupon, and then they will show you what they expect out of the casting.
Okay.
In other words, part of the qualification for the part or the material is that you will meet these lower specification levels from a test bar coming out of a casting.
Okay.
So I've seen those too. So there are engineers that understand the degradation of properties with section size and things like that. But, those are pretty sophisticated customers too, and they're not all that way.
Yep. The ones I run into tend to be the customer of the customer, the guy who bought the valve. And so he expects the valve properties to be the same everywhere in the valve, even though the people who design the valve know that's not true.
I think it behooves us to try to do our very best to be as good in the casting as we can be in specific areas, especially critical areas, to be as high as we can with these properties, to do our very best, regardless of whether we know they're degraded or not. I think we need to do what we can to get really good properties in our castings, period.
Yeah, I think that's right. One of the things that seems to me to be a real neglectful thing. I was talking to the expert designer who makes the Halligan bar, because we're doing in our cast in steel a Halligan bar, and so are the forging guys, and so are the additive guys for this next year. So the student teams will be making a Halligan bar, which is a big crowbar that you use to smash into anything where people are trapped when you're a firefighter. And the guy who's the expert designer said they tested investment cast bars and forging bars, and the cast bars will fail. I haven't been able to follow up with him, but when you look at a Halligan bar design, you're going to get shrink in the critical section where all that comes together. And unless people made some extraordinary effort to make sure it was sound, they'll meet all the properties for qualification. They'll meet all of the requirements for performance in terms of showing that the bar will work. But because it has that, when it fails, I don't know if it failed at the same load or close to the same load as the forging guy bent, but it means that castings get a bad reputation because we have a failure where the other bar just bends. And that's just unfortunate to me. We need to have that kind of premium product. And that goes to what you were saying, Paul, I think.
One thing that forging people have, and you're aware of this, is they can forge the part so it has extremely good properties where they're needed. Ours, when we make a casting, we have the same properties in all directions. But in general, some of those properties are less than what a forging is in a critical area if it's designed properly and designed so that the flow lines are consistent with the high stressed areas. So
Yeah.
that it's not unusual for me to see castings that fail when they're impact loaded compared to a forging in the same application. So that is not unusual for me to see that.
The big thing we've seen, Paul, with a casting forging comparison is the triple point microporosity, and the microporosity that's distributed throughout is an order of magnitude bigger and more frequent in castings, because forging really does crush most of that microporosity out. You still have it. You'll always see it in a fracture, but it's an order of magnitude less and much smaller. And when we've done the evaluations, that's really what we see the difference. So I would think in the Halligan bar that really it's the porosity you're going to have in that isolated heavy section that they're not feeding is what really the limit of performance is.
Yeah. And I think along with that, I keep talking about this, but the temperature gradient during solidification and the cooling rate have a huge effect on how a part like that's going to survive.
Oh, I think that's really critical. And that's what I want to do in our next session, is to revisit the sort of solidification patterns, because I think you're exactly right. When we looked at the armor stuff, it turns out that you really need the fastest solidification rate, which means you need the steepest thermal gradient if you want the maximum properties. Thermal gradient is pretty much the whole event, because the solidification rate is always fundamentally dependent on the thermal gradient adjacent to that section.
Raymond, I think cooling rate is important for the surface. To get the columnar, whatever you call it, the cell zones, to get it really tight and as deep as you can possibly get them. But when you're talking about lateral from one point to another point, then I think you're talking about the temperature gradient. And I think that both of those are important. I think if you have a good chilled surface, you'll have better properties on the surface of the casting where the stresses are high. But as far as having lack of shrinkage and small interdendritic arm spacing, I think temperature gradient is probably more important there.
Agreed. So, Caelan, you've been characteristically quiet. What are we missing? What is surprising to you? You came out of the mill products where you made perfect products and never had defects.
Right. So I suppose the first thought that's been going through my mind through all this is your very first reference was from 1936, and it's clearly stating that the test block doesn't necessarily mean anything for the properties within the casting. And that still holds true today. But I suppose the underlying thought and question is, has it gotten worse over the past 60 years in terms of customer education and understanding that to be the case? Or has it always been the case, and it's just an ever-present problem we face as an industry?
I think the answer is that it got lost with the slide rule. I think when you went from the analytical solutions, like Raymond said, you simplified apart to prismatic sections and easy to analyze, and used a slide rule where you rounded up every step and put a safety factor on at the end, where now you've got everything's engineered to the 32nd decimal point as if it's gospel, with no safety factor. You're just giving up safety margin that was kind of built into the old-fashioned process.
Yeah, one of the things, Caelan, I think is true is we've always had two different user communities. And so one user community are the people making pressure containing parts and airplanes and nuclear submarines, and they have to have the engineering sophistication. So they really have to grapple with these challenges. So even back in when we were using slide rulers, we still had the reputation that if it was simple enough, to use forging, then the forging was going to give me better properties. But if I needed geometry and it was complex and had complex loading where I needed a complex shape, a casting really was the premium product and could operate and could work. And so I think maybe really early on, people thought castings had pretty much the same thing, but we live within the legacy, even today, that we used to make steel with a puddling furnace where forging was part of getting rid of all the slag and making it a good product. And castings were gray cast iron, so they were always brittle, and you had to worry about sudden fractures. And so my dad used to tell me to be careful with the axe. If I chipped it with a rock, I might sharpen away the edge. And that had to do with blacksmithing, where steel was so valuable, they made the axe head out of wrought iron and they welded the edge on that was steel. And so the notion that he would have still had was that forgings, when you get it red hot and hit it, you're doing something to refine the metal, which is what the guy told me when we were talking about the Halligan bar, that, yeah, when you forge it, you're getting grain refinement, you're getting strength in a certain direction, and you have grain flow. And when you measure those things, they have very little impact on the actual mechanical performance. It's really the porosity and inclusion, the second phases that really dominate that. But it's really a fundamental problem. So I would say that in some sense it's gotten worse. What Jack says is true, but I think we've always had this bifurcation where you've got people who really don't have a strong materials background but are still designing equipment that aren't sophisticated, and so they assume properties are the same everywhere. And then you've got people in aerospace and nuclear that know the difference, and in some of the more sophisticated customers. So, Paul, you were shaking your head yes. Does that make sense to you?
Absolutely, I agree with that. Sure, absolutely. That doesn't mean we can't educate the guys that don't have the sophistication, though. Like, I think that's what Caelan's maybe getting to. Yeah.
Yeah, and I think that's one of the core things we're trying to do at Steel Founders, not only through these podcasts, but through a lot of the work that we're doing. And I don't think we're necessarily there yet, but you can't always just say that the customer needs to learn my product form better. Well, we have to do our best to make sure that we're making it easy to learn.
I think one of the things too is to remind these customers that what we're talking about are physical phenomena. They're not things that we have a choice in.
Correct.
You know, these are just pure scientific happenings. And please, when you design your product, remember this. This is something that it's not the fault of a casting, although sometimes it's. I remember one time a forging manufacturer that made blowout preventers said, "Can you stand the headache of a steel casting?" And yet all his annular blowout preventers were steel castings, so he had a lot of money where he could advertise and things like that, where we don't have that kind of, we don't do that sort of advertising. But that's the sort of thing that gets us in trouble, or not in trouble, but from a marketing standpoint is really hard for us.
Yeah. One of the things that was really good news this week is that we were finally successful at getting the carbon steels accepted in AWS-D 1.1, which is the fabrication standard. It's not complete yet, but we passed the last sort of vote on specification. So it looks like that will be in the next edition, that steel castings are part of AWS-D 1.1. And one of the things we want to do is have grades that are identical to the mill grades with NDT built into them, just like in the ASME boiler code, so that those engineers who don't want to learn enough to have the sophistication don't have to make judgments about the NDT level or what strength allowable to put into their design, that those are pre-selected for them. And since in most of those structural applications it's going to get bolted to the floor anyway, making the casting over designed by a factor of 20 or 30% is irrelevant. It just means another 3 pounds of steel in it. It really doesn't hurt anybody. And so I think those are some of the ways we're trying to grapple with that education problem.
I wonder, I should know this answer, I don't, but in Mike Quinn's casting design courses, is there a chapter on test bars? Or should there be one that kind of conveys all this so that customers who are learning about it get it in parallel?
I don't think so. And one of the things I was planning to do for the next series of webinars for our member companies was show some of the slides I showed you today, but really talk about test block and test block design and the variation of properties in test blocks. So these podcasts will really be helpful to me in refining what I'm going to do for them. But that's an interesting thing because we do have the test block document online, and I do need to update that as I go through test blocks again and bring it up to date with all these specification references. And there's a lot more material that I have now that I did when I was doing my PhD work, looking at the properties in, for example, structural steels, and they have the same kinds of property variations with the longitudinal and short transverse direction, exactly the same kind of property variation for the same reason. So I think that's something, but I don't think that there's a customer webinar on test blocks. So it may be that based on what the kinds of discussions we're having, I should do 2 or 3 webinars just on test bars, test blocks, and test properties. I think that would be useful.
The other thing is you may, I know you got a future leaders meeting coming up. That may be a good group to inoculate with these principles as well, as they're new to the industry and maybe in more contact with young people on the customer side and so forth. Just a thought.
I think that's right. Yeah, oftentimes what I'm doing with test blocks overlaps with the failure analysis stuff, because you really have to make people sensitized to the fact that failures occur because the component was loaded beyond its capacity. And the quality and test block issues are whether or not the performance limiting feature was something that caused it to fail below the design intent. And until you really grapple with that question, you really don't know what the failure mechanism is. And of course, we have an ordinary kabuki dance we do whenever a part fails. They call us up and tell us the casting failed. They bring us in and they show us the failure with some little piece of inclusion or porosity. We're pretty sure that it wasn't the cause of the failure, but they've got a technical report that says it is, and they're not asking for any money. So they tell us that we need to make our castings to higher quality, and we hang our head and we'll say, we're going to try really hard. And that's the resolution. And that's a standard practice. I remember Alex wouldn't accept that when he was at Mercury Marine. And so they bring him in and tell him that. And the customer would say, I want you only to give me your very best castings. And he says, I will be delighted to do that. I'm going to make the next 100 castings, and I'm going to have us do a critical analysis and rank them from the best to the worst. And you can tell me where the cutoff is, what you think is the best. You're buying all 100 of them. You're buying them all. So you can tell me. And the other thing he used to say is, I made it to your specification. This condition that you're unhappy with meets your requirements. If you want me not to put that in there anymore, just rewrite your requirement so that I inspect and make sure it's not there. They said, well, that's going to cost a lot of money. I said, you bet it's going to cost a lot of money. It's your money. You tell me how important this is. So those are a couple of things he used to do, which of course drove the design engineer nuts. But yeah.
I'll say that's true in the mill world as it is likely for every product form, because when you make bar that goes to get forged, they want that surface to be flawless, so there's no sort of indication on the surface that could pop open when they forge it. And if they see anything, It's a red flag. But if you inspect it, the depth of that indication might be much shallower than your requirement.
Yeah, yeah. Typical kind of problem. I think with the hollowing out of our industry and the demands that are going to be placed on us, people are going to have to become not only more realistic, but more sophisticated in understanding how they're buying and what we're making. But we'll see whether or not that pans out. Anyway, this has been a great session, I think. Really glad that we had this good time together. Interesting discussion. Look forward to our next time together. Please let me know if there are any additional information, things you need, any additional ideas that you have about other guests or things that you'd like us to talk about. Really enjoyed the day with our friends and hope that you found this to be valuable. Thank you.